DNI for solar energy applications from Earth observations.
Okay, hi. Thank you. My name is Calvin. I am a PhD student from the Grantham Institute at Imperial College London and the UK National Centre for Earth Observation. So today I'm going to talk about developing automated methods to estimate spectrally resolved DNI, direct normal irradiance, for solar energy applications. So this morning we've heard a lot about sustainable development goals, and one of the plethora of SDGs is about affordable and clean energy. And in that context, and along with things like the Paris Agreement, has led to an incredible drive towards renewable energy adoption over the past decade. And solar technology is an incredible part of that. So we see a lot of solar panels around, including actually outside, as well as walking from the metro's station. But most of the solar panels we see around roadside and on rooftops are what we call single junction solar cell. Single junction in the sense that there's a single layer of semiconductor, typically that of silicon. And because there's only one layer of semiconductor, the spectral response of these devices are usually relatively simple. And the typical efficiency of these things are only about 20%. So good, but not great. We can do much better. The state-of-the-art in terms of solar technology these days are called multi-junction solar cell. So this is a commercially available triple junction cells. Whoops, what did I do? There we go. Yeah. So, and the triple junction cell, each of the layer here is designed to absorb a very specific slice of the solar spectrum, thus maximizing the utilizable part of the irradiance. And because of that, the numbers are much bigger. So 30% for commercially available CPVs, and 46% is the world record done under laboratory condition. Now, to achieve these numbers, these cells are typically topped with an optical concentrator to focus the irradiance beam 100 or 1,000 times. And that has interesting implications, as we'll see later, on how we count up the number of photons that these devices can see. So if you put some numbers here, so if we define an aperture half angle here, we can see that depending on your assumption and the way the solar cell is designed, it can range from anything from almost 0 to 2.5 degrees, 3 degrees. But the bottom line is that these things have nuanced and complex spectral responses. Now, unfortunately, all existing multi-junction cells are designed against a standard spectrum. So this is an example that's widely used within the photovoltaic community from ASTM. It assumes, amongst other things, a low aerosol optical background, which is can be very unrepresentative of the actual climatologies in which many of these solar cells are being deployed. And previous studies have shown that there can be up to a 75% deviation in the simulated energy yield if we assume set spectrum. So this is where we can come in as Earth observation people. So no matter whether you are talking about fixing a particular location in climatology and want to say, oh, how do we optimize our solar cell design? Or you're given a solar cell design and you ask, okay, where's the best place in climatology to deploy these cells to maximize on return on investment and so on. We need a very precise and accurate map of spectrally resolved direct normal irradiance. So hopefully that convinced you the importance of estimating these quantities. And so in the remainder of this talk, I'm going to talk about 4 different schemes to estimate spectrally resolved DNI. They're not kind of independent schemes, they're kind of like one building on top of each other, accounting for more and more things. And they're all based on the standard literature approach of a radiative transfer model. So to begin with, we realized that actually the ground albedo, so the ground reflectivity, doesn't matter for these CPV devices, which is quite important because it simplifies the problem quite a bit. Next is to account for species that are relevant in the shortwave regime, things like ozone and water vapor, which we've taken from our ECMWF integrated forecasting system. Here are some simulation we have done to show the impact of precision of ozone and water vapor profiles on the DNI, spectral DNI that is being estimated. So you can see there's some sensitivity here, but they are relatively not so important when compared to, plotting on the same scale, the effects of aerosols. So here we have fixed the, we varied the type of aerosol in the atmosphere in our model, and just to show that how sensitive the spectral resolved DNI and thus the performance of these solar cells are to the aerosol type. So we can see inappropriate assumptions about the aerosol in the atmosphere can lead to 150 milliwatt per meter square per nanometer difference across the spectrum. So that convinced you, hopefully, that aerosol is important, so let's put aerosol in. So as a first step, we kind of prescribe it a priori in our model based on some climatology. Lastly, we have satellite observed extraterrestrial irradiance. So that kind of completes the first sort of baseline scheme we call the climatological aerosol scheme, hopefully for obvious reasons. So we can do better than this. So the second scheme we call the spectral aerosol classification scheme, where we sort of iteratively vary the aerosol type in our model until we find one that sort of optimizes and matches, best matches our observation, whether it's ground-based observation or satellite observation. And then the next scheme here, we add an extra component to it, which we call loading optimization. So in a similar spirit, once we've determined the type of aerosol in the atmosphere, we iteratively vary the amount of aerosol in our model until, again, we find the best match spectral behavior from the observation. So these two steps are relatively sort of standard in terms of satellite retrieval. But the interesting thing, I think the interesting thing we've done here is to do the statistics that are sort of relevant on the spatial, temporal, and spectral resolution that are relevant to solar farms and solar cells. Lastly, the last scheme here, we have taken into the circumsolar factor, which is related to the optical concentrator that I mentioned earlier. So just to remind you, like that. Basically this factor is sort of correct for the circumsolar contribution. And the way we do this, we compute something called the circumsolar ratio. It's a percentage contribution from the circumsolar region to the direct beam. So here are some numbers here. Going from left to right is increasing in Zohr zenith angle. From top to bottom is increasing amount of aerosol optical depth. And different colors represent different aerosol type. So for, if the atmosphere is relatively pristine and the sun is relatively high, the circumsolar contribution is, not very important. But otherwise, actually, it can contribute up to, 1%, 5%, and in extreme cases, 10, 20, 30%. So this is what the circumsolar factor correction is doing here. Okay, so that's enough about the schemes. Let's look at some, let's look at them in action. So we validated these schemes against a few sort of case studies. The first one we've done is against Santiago, Chile. Reason is because we have some in situ measurements there to validate our scheme. It also has relatively complex aerosol climatology. There's the ocean, the urban industrial area with forest fires and desert to the north and things like that. Well, not the forest fire in the city, but around the area. So that's that. And here are some of the results. So the red line here is showing the climatological baseline scheme, and going sort of blue and then orange and red is sort of subsequent schemes. So you can see when we sort of take a climatological approach, we get a bias of about 4.5%. So 4.5% doesn't sound like a lot, but if you're operating $1 billion solar farm, that can add up really quickly over the years. So and if we do the aerosol optimization and so on, and accounting for the circumsolar factor, we can see that we get much better accuracy and precision. This is just showing how the circumsolar factor works. So this is the above plot is the error distribution before we account for the circumsolar factor, and after at the bottom. So you can see we kind of move the distribution narrower and move it closer to 0. The second case study we've done is at NAMI, which is completely different aerosol climatology, so it's a good case study. There's desert events and and so on, a lot of mixed type aerosols. And so similar to the previous plot, but this is for a different site. Again, you can see the climatological aerosol scheme sort of consistently sort of underestimate by about 20, 30 watt per meter square, and the our sort of the best scheme we have actually estimated pretty well, so 0.3 watt per meter square over 1,000. So that's a pretty good accuracy and precision. So just to show you, this line here is showing the standard irradiance spectrum. So this is what the photovoltaic community has been using to estimate, to rate and design the cell. So you can see it's actually, it's pretty poor. So that was against the broadband irradiance, but we are talking about spectral radiance. So fortunately, at NAMI, we have some spectral measurements. So this is, again, plotting the difference between our estimated DNI from observation, and you can see they align pretty closely with error under 1%. Cool. So just to quickly conclude, we have developed an automated method to estimate spectrally resolved DNI. We sort of, the main approach here is use spectral aerosol classification that takes multi-spectral AOD, and we sort of illustrated the importance of accounting for circumsolar factor, which depends on aerosol type, and that can come from Earth observation. Moving forward, ideally we want more measurements to validate our scheme. But the more interesting thing is to feed these into solar cell models. So we've been working closely with the photonics group at Imperial. They develop models and simulations to take these DNI measurements and actually turn them into power estimates and turn them into sort of, they have code to optimize the solar cell design based on our output. And lastly is to move towards, so what I've been showing you previously are all ground-based measurements. So is to move towards satellite retrieve AOD, and for that we've been working with people at ORAC in RAL space. So trying to couple these DNI estimation scheme into the satellite AOD retrieval, so that these DNI, spectrally resolved DNI, can be routinely generated for the photovoltaic community. And that's that. Thank you.
Thank you very much. So can we have some questions, please?
Cheers. What optimization methodology did you use?
So I mean, it's basically just minimizing the root mean square error across all the wavelength channels. But I mean, the optimization algorithm is pretty standard.
Was there an intelligent component to it? I'm thinking about Bayes' global optimization, where you've got some idea of where to set up your next experiment to get the most information.
That's something we haven't looked into, but yeah, happy to talk to you. Actually, quite interested because I'm like right now thinking of other places to validate our scheme, and we're trying to contact with different solar farms to see whether we can work with them as well.
Can significantly reduce the cost.
Exactly. The interesting thing is that these spectrally sensitive solar cell, they're kind of like ground-based sensor in a way. So yeah. Yeah.
The question's not about energy, but about agriculture. Do you think there might be a transferable scheme here for understanding crop productivity?
Yeah. So spectrally resolved irradiance is also important for photosynthesis. So there are a lot of studies out there done previously to look at the photosynthetically active region of the solar spectrum to predict, not necessarily agriculture, but just crop health and things like that. So yes, so there are studies that are done. The interesting thing is that the spectral resolution and range you need for understanding how photosynthesis will perform is quite different from these solar cells. So the spirit is similar, but yeah.
Any other questions? Yes.
What about cloud?
Cloud. So far we have only been looking at cloud-free conditions. So these CPVs, they're only really relevant for because they only take direct beam, unlike silicon cell, which can take diffuse, so they can work cloudy conditions. These things can only really work under cloud-free conditions. So we have not really looked at clouds, but some literature suggested that the circumsolar factor actually it's quite important when you have high, thin, cirrus cloud and things like that. So that's definitely something that needs to be accounted for. When these things need to go operational and things like that. Yeah.
Excellent. Thank you very much, Kelvin. Okay, so on to our next speaker. If we can get David Cotton up, who's going to be talking about